would like to introduce very shortly Professor Mike Jenkin is distinguished professor, who is organizer of statistical program. I believe that part of this course will be done by you, but by your colleagues. I hope you will enjoy this course.
Okay, thank you, Mikhail. So hello everyone, welcome to this short course. I'm pleased to see so many of you here at KAUST for this couple of days. So this short course today is about large-scale spatial data science with ExaGeoStat. So the short course is a joint effort with my colleague, Dr. Sameh Abdullah. He's a research scientist here at KAUST, and Dr. Yen Song, who's a postdoc in my group, just coming here. So today we're going to share the presentation between me and Yen. This is also in collaboration with other colleagues, Professor Ingsun, Dr. Hatem Taif, and Professor David Keyes, who will speak later today, as I understand. So my group here at KAUST works on spatial temporal statistics and data science. This is the link to the website. And in fact, I have put a copy of this slide on this website. So if you go to this link here under teaching, you will see the slide for this part of the course today. Okay, so you can download the slide, you can follow now with them if you wish, or you can look at them later on as you like. So this short course will have 3 parts. The first part today is going to be an introduction to spatial statistics, spatial data science as a motivation to the type of problem we're trying to answer here. The second part tomorrow will be about high-performance computing. This will be given by Dr. Sameh Abdullah. This is a very exciting topic. I'm sure you will like it. He will talk about the supercomputer here at KAUST and other supercomputers in the world where we have been running some of the experiment related to this project. And the third part on Wednesday morning will be about demonstration examples of how to use the software to do this, to solve this type of problems that we have here. So in the title, there are basically 3 things. There's spatial data science, and I will tell you today a bit what this is about. There's the word large scale, so we're going to be working with very big data sets. So that's the meaning of large scale. And ExaGeoStat is a software that we've been developing here at KAUST for the past 8 years. It stands for Exascale Geostatistics. So it's geostatistics or spatial data science for very large data set. And I will tell you more also about the software during this short course. Okay, so the first part today will be about the spatial statistics overview. So that will be the focus, to give you some background about this area and why these are interesting problems and what are the challenges that we find there. Before we do that, I just wanted to tell you a little bit more about myself. I grew up actually in Switzerland in a very small village, probably smaller than Thule. Maybe 1,000 people live there, so I went to school there. And then I went to the Swiss Federal Institute of Technology, or EPFL, in Lausanne to study applied mathematics. So that was my passion. And I was interested in many topics. In particular, I was interested in PDEs. And I thought it was great. But at some point, I thought, well, what I'm going to do after I finish these studies? And I thought, well, maybe if I learn more about statistics and data science, it will be easier for me to find a job. That was my thinking at the time. So this is what I did. And at some point, I found a professor who I like, because if you're going to do a PhD, you have to find someone you like to work with, because you're going to spend 4 years typically with this person. So this is what I did, and I kind of focused more on statistics with the aim to work in a company after getting my PhD. But my plan didn't work like this, because I got an offer to go to MIT in the US as a lecturer in statistics. So this is what I did. So I went there, and once I was there, I spent 15 years in the US I went to North Carolina State University and then Texas A&M University, and that was at the time when KAUST started, and somehow I had the opportunity to come here in 2012 and build a statistics program from scratch, and so this was a very appealing experience for me to have, so I came here to do exactly this. So my research interests, just very briefly, are mainly about spatial temporal data. Also, I'm interested in robustness issues and non-Gaussian distribution. And in particular, I'm interested in application in environmental science and climate science. Also, I like to look at data from renewable energies such as wind and solar power. And this is very relevant for Saudi Arabia, so I have a big project on this topic here at KAUST. So this is about myself, just to give you some information. So let's start with the short course. So let's talk a little bit about spatial data. What do we mean by that? So by spatial data, we don't mean data from space, from the moon, Mars, or other planets. It's not about that. We talk about spatial data when we have data that are indexed in space. So this means every observation has coordinates in space attached to them. What would be an example, you think? If you measure temperature, for example, you measure temperature here in KAUST, but in Tuol, in Jeddah, in Riyadh. In each observation of temperature, you have a coordinate associated, and you can say where this temperature has been recorded. Okay? You can think also about the cost of housing. Maybe it's different if it's here at KAUST in Tuol, or in Riyadh, or in New York, or Australia. So there's a coordinate location attached to the data of interest. So by this, we mean spatial data. Now, we have different types of spatial data. The focus here will be on what are called geostatistical data. This means that these coordinates, they can vary continuously in space. So in principle, you could take a thermometer, and any possible location in Saudi Arabia or in the world, you could go with your thermometer and check the temperature. Right? So you can vary this index, these coordinates, continuously. Now, if you think about the type of spatial data that you could collect, what do you think would be reasonable ways of collecting spatial data?
Well, going to that location and collecting the data.
Yes.
Recording that this data is at this location.
Yes, but what kind of instrument would you use?
It depends on the type of the data that you want to collect.
Yes. So you can think about having devices like sensors, for example, that will record temperature that you can place at different locations. So exactly at this location, they will record temperature. But you can think also about other ways of collecting data. For example, with satellites, you take images, and the color or the scheme of the image will tell you something, some information about, for example, temperature in a larger region, possibly, not just at a point. So this means that some measurements are actually point measurement, for example, with a sensor, or you have what are called aerial data, so a satellite with an image maybe has a certain resolution and can only cover a big area, but you cannot say very precisely at a point what the temperature would be. This data could be regularly spaced, so if you think about satellite, an image, you discretize it with pixels, so you have a kind of regular grid. But if you put monitors at different locations, in general, those are irregularly spaced, so you don't have necessarily a grid of location. These data, they can be just one variable, so univariate like temperature or the price of houses, but often they're actually multivariate because you observe with your sensor not only temperature, but also pressure and pollutants, so you have several variables, right? So the data can be multivariate. They may evolve through space. So you have spatial coordinate, but often you have also a temporal coordinate. So at a certain location, for example, in KAUST, what's the temperature now, but it evolved through the day. So you have also a temporal component. Some data are directional. So if you think about wind, There's the strength of the wind speed, but also a direction. Often here in Saudi Arabia or in this area, it blows from the northwest, but sometimes from the south or from east, and then gets hotter, for example. So there is a direction. And if you think about data about the Earth, so if you want to study the climate, for example, typically we use climate model to simulate the climate on the Earth. The natural geometry of the Earth is a sphere, and therefore the data are located on the sphere. Okay? So you can think about this different type of data that we could be collecting. There are other types of data called lattice data and point patterns, and we don't cover those in this particular short course. But one of the most important rule here is this so-called law of geography that says that nearby things tend to be more alike than those far apart. So this is a very fundamental idea and very intuitive, I think. Namely that if you record the temperature here at Kaust and in Tuol, well, the two locations are quite close to each other, so probably they are very similar. Maybe not exactly the same, but about the same. But if you look at the temperature far away from here, for example in Riyadh or in New York, well, it's likely to be quite different. Maybe they are not very related, whereas between Kaust and Tuol, because they are nearby, they are more related. So that's the idea. So we want to use this information to basically be able to predict the variable of interest, for instance, temperature, in different locations in space.
A question.
Yes?
Like there is a fixed distance, and like if I want to collecting data for over there or something for temperature, like there is a fixed distance like to sample data.
Yes, so the question is whether there's a fixed distance between the data, right?
Yeah.
So this depends a bit on the way you collect data. I mean, typically you would put monitors at different locations, and the distance is dictated by the distance between the monitors. Okay? All right, so as a motivation, let's look at this data example here. This is wind data, wind speed data, hourly actually, in Saudi Arabia in June of 2010. The data are taken at 28 stations. So this station record the wind speed, for example. In fact, not only speed, also the direction and other quantities. But let's focus on the wind speed. The different rows represent different time. So let's look at the first row, the first time. The data would look like this. So you have a map of Saudi Arabia. You have these dots that represent the 28 locations. They are colored in a color that represent the speed, the strength of the wind speed. So you see the closer to yellow and light green, the lower the speed, and the more blue and dark, the higher the speed of the wind. So you have this information at this 28 location, and you can see some structure. There is some kind of dark blue here, and much more light green here or yellowish. And you have to know that if you have a wind farm with a wind turbine, you need typically, depends on the turbine, but about 4 meters per second wind for the turbine to start to rotate and then to produce electricity. So the question is, if we observe this wind speed at this 28 location, what can we say about the wind speed at a new location where we don't have observations?
If it is near to
Hmm?
If it is near to the observed location, it will have a higher speed.
Yes, so if it's near, you would expect that it will be similar, right? And if it's further away, it will be more different. But the question is, can I take any point in Saudi Arabia based on this data and say what the wind speed would be there? So I need a method to do that, basically to interpolate between these different locations. And this is what we're going to be talking about, how we do that. A naive way would be to do what?
Classify something. You can use
Nearest neighbors? Yes.
Maybe just grab it between 2 points and average it out.
Yeah, take 2 points, average. Well, you have 28 observations. I mean, one very naive way is to say, well, just average all these 28 observations, and that's my best guess for the wind speed, right? But this would mean that at any location in Saudi Arabia would be just this one number, the same everywhere. And it's not quite like this, right? So again, this law of geography should tell you that observations that are close to each other will tend to be similar. So we have to take into account this dependent structure in space. So this is what we're going to do. So the method here, I'm not describing it in detail, but the method that we'll use you can have a predicted mean wind speed. So this is the map here. And then you can also give quantiles, so a low quantile of 5% and a high quantile of 95%. What would be the wind speed, very low or very high? What are kind of bounds for this? And this we can compute as well. And here I put a reference where there's some more analysis about this particular data set. But that's the basic idea. We want to be able to predict at a new location. So how do we do that? So to do that, typically we use what are called stochastic processes or random fields. They are basically random variables, but that are now indexed in space. The simplest is actually the case where the index is time, like a time series. So you observed Z would represent temperature, now at a fixed location, but over time. But in our case, the index is space, so S is for space. So the index S belongs to a region D, typically in our D where D often equals 2, say, for practical reason here. And such a process, a spatial process Z of S, is called a random field. Now this random field can have different type of distribution, but one of the simplest and most popular is called Gaussian distribution. So those are called Gaussian random field. And such a field is Gaussian if all the finite dimensional distribution are multivariate normal. So this means that if you're given any set of location S1 to Sn, and you observe your process, your random field at this n location, you put them in a vector, this vector should have a distribution that is Gaussian, that is multivariate normal. So that's what is called a Gaussian random field, and we'll focus on this type of fields for now. And these fields, they are completely determined by the mean and the covariance function. So the mean is kind of a trend. So it could be, the mean could be constant over the region, over Saudi Arabia, or increase from east to west, for example. There could be a structure in the mean. But the most important for us here is to focus on the covariance function, so the spatial dependence that tells us how the dependence changes as a function of the distance. So this is what we're going to try to model. So the mean function is just the expectation of the process Z at location S. So it's a function of the location S. We call it mu of S. And the covariance function is the covariance between Z at a location S1 and Z at another location S2. So you pick two locations, S1, S2. Z is, for example, temperature, and you want to describe what's the covariance between temperature at location S1 and temperature at location S2. This, by construction, in general, is a function of the two locations S1, S2. And the definition of covariance, if you had a basic course on probability and statistics, is just this. So we'll be interested in modeling this covariance function. So here is an example where you have some data. So the scale is represented by the color bar on the right. This is actually data on Earth. So the domain of the random field here is the sphere. This has been projected on this rectangle, and you see the different country borders. And now the question is that if you have two locations represented by these crosses, what's the covariance between the variable at this location and this location? How can we calculate that covariance? How can we estimate it? Well, to estimate something, usually you need replicates in statistics. So you need several observations. But here we have only two observations at these two locations. So we cannot estimate the covariance directly from just this data. So what we need to do is to try to create more data, and we do this by assuming structure on the covariance function. So this is this notion of stationarity. So you can distinguish between strict and weak stationarity. For Gaussian processes, Gaussian random field that we consider, they are actually equivalent. In a nutshell, what this means is that the mean function is invariant through shifts by the vector h, and the same for the covariance function. So if the mean is invariant by shifts, this means that, in fact, this mean is constant over the domain. And if the covariance is invariant by this shift, this means that it depends only on the shift between S1 and S2, so only on the difference between the two locations S1 and S2. This is the notion of stationarity. And this difference is a vector, so still has a direction, but some covariances are even isotropic, which means that it depends only on the norm between the two locations, so exactly the distance. So this means that if you have a location S1, all the locations around on a circle at a certain distance are going to be the same. That's what isotropic means. It's a simplification of the covariance function, and it's not always realistic. We can relax it in some ways and in some settings, but it's useful to create more data, basically, to estimate the covariance. So we're going to use this assumption for now. Yes?
Does it give only one number or one estimation or a multiple estimations? One value or a multiple values?
No, for all the pairs of location separated by the same distance, the covariance should be the same. So all these pairs of observation help to estimate the covariance for that specific distance. And then you can do it for different distances. Yes.
How is this difference between K and N?
KNN doesn't model the covariance, for example. Here we're going to model explicitly that covariance function, as I will show you.
The main idea is the nearest neighbor and have the same class or...
Yeah, so you could say, okay, at a new point, I just take the 5 nearest neighbor and I average them and I say that this is my prediction. You can do this. But this is not the optimal prediction. We're going to say what's the optimal way to do this prediction. Okay, so this covariance function C that we want to model, it needs to satisfy certain properties. The most important is that it has to be non-negative definite. This means that for any integer n, any location S1 to Sn in the domain D of interest, any real number C1 to Cn, this double sum over J and K of this quantity, so the covariance at location Sj and Sk with this real number as factor Cj, Ck, this has to be positive. So this means that we cannot take any function to model the covariance. This function has to be a non-negative definite. In fact, often is a strictly positive definite function. We cannot take anything. So we're going to use model that we know we can prove are positive definite and are valid model to describe the covariance. This positive definite function have many interesting properties. For example, if you take a sum of two positive definite functions with positive coefficient, the result is still positive definite. Or if you take the product of two positive definite functions, the product is still positive definite. And in fact, the limit of a sequence of positive definite function is also positive definite. So all these properties are useful to build new covariance models. So why do we care so much about the covariance? So here's an illustration for that. We have two data sets here, one in panel A and one in panel B. The one in panel A, in fact, every point is independent of any others. So there's no structure here of the data. In panel B, nearby points have correlation, so they tend to be more alike. This is this law of geography. So this means that in a region where the points tend to be red, so high, others are also red. And in a region where the point tend to be low, here negative, then others tend also to be low. So this means that now if, say, in this setting of data, this pixel, this blue pixel here is missing, and you need to predict it, then what's your best guess for that? There is no real structure, right? Next to a blue could be a red. There is no structure in space. So you could put any of the observation there or just take the average, and this will be good. But if you're in this setting B, and let's say this red point here is missing, then what would be your best guess? Yeah, it seems like nearby points are kind of red, so the best guess is probably red. It's quite unlikely that suddenly it would be blue there. It could be that the dependence actually is strong, so that the nearby points tell you that it should be red. So that's exactly what we want to use. We want to use the covariance function to tell us how much weight we should give to different observations. And the stronger the correlation, the stronger the weight we should give. That's the intuition. This leads to this notion of kriging. So kriging is the idea of spatial interpolation, so predicting at new location what the variable of interest would be. This is named after Daniel Krieg, who was a gold miner in South Africa, and he kind of invented these ideas and these techniques to do the prediction. Kriging means basically the best linear unbiased prediction, or BLUP, to predict the variable of interest at a new location. So let's say that you have a new location S0 and you want to predict the variable Z, so Z hat will be the new predictor. We want it to be best linear unbiased prediction, so linear in the sense that it's a weighted sum of all the observation we have with weights lambda I that we need to define. We want it to be unbiased, so the expectation of this predictor Z hat should give us the mean at this location, mu at S0, and we want it to be best. Best in what sense? In the sense that the variance between the predictor and the true unobserved quantity at this location, we want this variance to be as small as possible. So best in this way. So this problem is actually an optimization problem that you can solve. And the solution, what we want to find are these weights, this lambda I. The solution of this optimization problem with constraint to be best and unbiased, in fact, is the solution of a linear system that depends on the covariance function. So these optimal weights to do the prediction are function of the underlying covariance function. So this is why we want to model this underlying covariance function. That's the idea, so that we can do prediction in an optimal way. So there are different models of covariance function. As we just saw before, we cannot take any model. It has to be a valid covariance function in the sense that it has to be positive definite. So you can study in mathematics what are model of positive definite function. And here's a popular model called the Matern covariance function. And it says that the covariance of the variable Z at location Si and Z at another location Sj is described by this function. You see that it depends on the norm of Si minus Sj here and here. So it depends on the distance between the two locations. It involves a Bessel function. So this is a function that is a bit complicated, and some other quantities. It has 4 parameters. Sigma square, which is called the partial CIL. This beta that controls is called the range parameter, controls how quickly the covariance or the correlation goes to 0 as a function of distance. We would expect when the distance is very big that this correlation goes to 0. This is the law of geography. The smoothness parameter nu, here this order and this power here, control how smooth or rough the realization are. And the nugget effect tau square, which measures microscale variability In fact, the variance of the process is the sum of sigma square and tau square. So we want to learn these 4 parameters from the data. If we learn them, if we estimate them, then we can use that covariance model to do the prediction, to find these optimal weights and to predict the variable of interest at any new location in the spatial domain. This is what we're trying to do. It's useful to talk just very briefly about this idea of effective range. So the range parameter beta controls how quickly the correlation goes to 0. We can say that basically when the distance is infinite, this correlation becomes 0. But we want a finite distance at which the correlation is small. And for example, we say a small correlation would be 5% of correlation. So if you take a unit square as the spatial domain, you could say that the strength of the dependence is weak, medium, or strong if this effective range is, for example, 0.1, 0.3, or 0.7. So if you think about the unit square, 0.1 to 0.1, from 0 to 1 and 0 to 1, a distance of 0.1 is very small, right? So you would say this is weak dependence. A distance of 0.3 is kind of medium, and a distance of 0.7 is kind of strong. Okay, so that's a classification, if you want, of different type of dependence. So now this model, this Matern covariance function that I showed you previously, here I have plotted for 4 different values of the parameter nu controlling the skewness. So this parameter nu is a real number between 0 and infinity. When it's 0.5, in fact, this model, this Matern model, this simplifies to just the exponential of minus the distance. So this means the covariance or correlation decrease exponentially. So this is plotted here, in fact. When u equals 1, this is called the Whittle model, so it's plotted here. This is for nu equal 1.5, and this is the value of nu equal to infinity. In this case, the Matern model simplifies to what is called a square exponential. So it's exponential minus the square of the distance. In each plot, there are 3 curves, red, blue, and green. You see that red corresponds to strong dependence, medium to blue to medium dependence, and green to weak dependence. Indeed, if you look at the red curve, for example, you see this is correlation, right, between 0 and 1. It decreases, so horizontally you have distance. It decreases as a function of distance, and this horizontal line here is actually at 5%. So this red curve crosses 5% at 0.7. This is what I said would be for strong dependence, 0.7. And this is the same for all 4 red lines. This one here crosses at 0.7, this one here as well, and this one here as well. So all 4 red curves correspond to strong dependence. What is different is the way they behave at the origin. So when the distance is close to 0, you see for this case, the way the red curve leaves the value of 1 is kind of with a horizontal tangent. So it goes like this and then down. Whereas this one here goes linearly down. And this behavior close to distance 0, in fact, controls or dictates the smoothness of the realization of the random field. So now, finally, I'm going to show you realization from Gaussian random field with this type of Matern covariance function. Here are some realization. So each realization is on the unit square, from 0 to 1, 0 to 1, with a color scheme that is given here on the side. The first column corresponds to this parameter nu equal to 0.5, so this is an exponential. So when this parameter nu is small, the realizations are rough. So if you go from left to right, you see that you go from, so here on the left, the realizations are very rough, and here they are very smooth. So this parameter nu, first column is 0.5, second column is 1, third is 1.5, last is infinity. So this controls how rough or smooth the field is. When you go from top to bottom, the different rows correspond to the different strengths of dependence. First row is weak, medium, and strong. You see it very well here, for example. Here the dependence is weak. This means that if you have an area with kind of high value, red, it's short-lived in space. Here the dependence is medium, here the dependence is strong. If you have an area that is red, then for a long time, for a long area in space, it remains red until it changes. So that's the strength of the dependent. Strong, so big red blob or a big blue, for example. Here medium, up small. Okay, so the idea now is that if we have data from these different stations, we collect the data, we want to learn the parameter to know what kind of random field we're going to have, right? So with that we can do prediction at new location and build these maps. Any questions so far on this? It's okay? Yes? From right to left? So from right to left is the smoothness. So you see that here things are very smooth, so the change is very gradual, whereas here there is a lot of mixing of red and yellow, it's rough. So here very rough, a bit less rough, a little smooth, very smooth. Okay.
The desired, the smoothest or?
Nothing is desired. I mean, we try to figure out what the data will be. We want to model the data. So let's say we take the wind data. If we fit this Mattern model and we find that the estimates correspond to a field like this, then this is the model we're going to use to predict the wind speed at new location.
So by increasing the mean to be more smooth, right?
Yes, if you increase the parameter nu, the realization of the field become more smooth. Yes. Okay, so now this was for just one variable, right? So I said earlier on that there are, in practice, many cases where you have more than one variable. So then you have to worry about what would be the covariance in this case. So I will not spend a lot of time, but just tell you that you can also handle this situation. So if the random field now has p different variable, if p equal 3, it could be temperature, pressure, and wind speed, say, p equal 3, then this covariance function becomes a matrix of dimension 3 by 3. It's called the cross-covariance matrix. And now each entry describes the covariance between the variable zi and the variable zj at two different locations. So let's say you have two different locations. You have temperature at this location, and you have pressure at that location. And you want to say what's the covariance between temperature and pressure, but at different location. Of course, you want also to know at the same location what's the covariance between temperature and pressure. And you want also to know what's the difference, what's the covariance between temperature and temperature at two different locations as before. So you see that things are a bit more complicated now because we have more covariances to consider, because we have this p by p matrix if we have p different variables. So we have a more challenging problem. We have to come up with models that will lead to positive definite matrices. And so this is more challenging to find mathematically what kind of cross-covariance model will be valid model. And there are some references here if you're interested to read more about this specific topic. So the bottom line is if we have more than one variable, we can handle this as well. But of course, things become even more challenging than the previous case.
There is like an error rate for this one. There is an error rate like to calculate it.
To do what?
The error rate.
Yes.
Like I can like calculate it or it's always correct.
Yeah, I'm not sure exactly what you mean, but no, it's not always correct. I mean, these are
How could I know?
yeah. So these are models. These are models that have certain properties, and you need to figure out from the data if this data will satisfy this kind of properties. So the model is never perfect, right? So it's always an approximation of reality, and we want to find models that are more and more realistic for the data at hand. So we want to find models that are better and better, but often they become more and more complex as well. So yeah, there's a lot of research in how to construct more and more realistic such cross-covariance model. And it's not easy because this model have to be valid, need to lead to positive definite matrices, and mathematically this is a bit challenging to come up with valid models. Yeah. So that's the multivariate case. There is also the spatial temporal case. So as I said earlier on, if you have information in space, often it evolves through time. So then the covariance function is a function not only of the lag vector h in space, but also a lag in time. So u represent the difference between two time points. So we can also build covariances for space-time data. The simplest are so-called separable models, where you take a covariance in space, like we had earlier on. You take another covariance just in time, you multiply them. We said from the properties of positive definite function, the result is guaranteed to be positive definite. So the result is a valid space-time covariance function that will be positive definite. Unfortunately, if you do that, this is not very realistic because this means that space and time do not interact. And often in practice, there are space-time interaction. So people have looked at more complex and challenging models that would allow the space and the time to interact. For example, in this model, you see that here the time is from the lag u, so it appears here and here, and the space is from the lag h, it appears here. So you see here you cannot really separate space and time as a product, so there is interaction. But also here there are parameters. For example, this parameter beta, if this parameter beta is set to 0, this disappears. This becomes 1, and then you have separated the space from the time here. So the separable model is a particular case of that non-separable model. So the bottom line here is that if you have space-time data, you can also model it with space-time covariance functions. And essentially, you can do the same type of problem to do kriging prediction, not only in space, but in space and time based on this kind of models. So this is basically a brief introduction on this idea of dependence in space, covariance function. The basic is just in space, but it could be extended to multivariate and space-time, and we have this in the software that will be presented later on in the short course. This covariance function allows us to do spatial or space-time interpolation, so to predict at new location in space or in space-time where we don't have observed data. We want to do this prediction at many locations so that we can draw a map. Solving for these weights in kriging means that we need to solve a linear system. The size of the linear system will depend on the number of locations, the value n. So when n is large, this linear system will become large to solve. So maybe this becomes problematic. And now what we haven't discussed yet, but will be in the next part, is how we do inference. So how do we estimate this parameter from the Matern covariance model based on the data? And you will see that the method that we prefer, the so-called likelihood-based method, will involve this big covariance matrix of dimension n by n. And when n becomes large, it will be very challenging, for example, to calculate the inverse or the determinant of that big covariance matrix. And this is part of the challenges that we want to address with this software ExaGeoStat. So now is a good time if there are any more questions on this part before we switch to the next part with Yen. Any question?
Can you please provide examples, like real-life examples on the spatial temporal models, like where we can implement these type of models?
So you could have a monitoring station that record pollutants, different pollutants, okay, at different spatial locations, but they will evolve through the day, so they will change through time, right? So this monitor, for example, every hour they record pollutant, and then the data are space-time, right? So then you're interested in forecasting, for example, at a new location, what would be this pollutant? What's the best guess for the value of this pollutant? Okay? Or the setting about wind speed, the interest there is to predict the wind speed, for example, in 4 hours from now, right? So you can measure what's the wind speed now and in the past, and maybe at neighboring location, and you would like to know here in 4 hours from now what would be the wind speed. Often you need to know that because if there's a lot of wind, then you're going to produce electricity from the wind farms, and you can put it in the electric grid and use it. But if suddenly you forecast that there will be less than, for example, 4 meters per second, the threshold for the turbine to rotate and produce electricity, if you can forecast that there will not be enough wind in 4 hours from now, you can say, well, I will not have electricity from the wind farm in 4 hours, so I need to use something else. So there are many problems of this type where you want to forecast in time, but also interpolate in space and new location to know what's the variable of interest.
Is there any assumptions on the data?
Assumption on what?
On the data.
Yes, so the type of model that we use, here we talk about Gaussian random field. So this means there is an underlying assumption of Gaussian, of normal distribution for the data. In some cases, it's reasonable, but not always. So you need also to develop non-Gaussian model that can account for this departure from Gaussianity. In fact, we have some such model also implemented in the software to deal with skewness and heavier tail in the distribution of the data. So yeah, so that's an assumption that is made, the assumption of Gaussianity. Yes.
How do you implement like one of AI models for maybe temperature, and how different from these techniques?
Yeah, AI model is a very generic name, so I mean it could be basically anything. We have
For prediction temperature.
yes, we have run some competition here in Chaos. It will be mentioned in the next part, and we had some participants using machine learning and AI-like method, and they didn't perform that well. But there's ongoing research on trying to merge ideas from the spatial data science with machine learning method to improve the forecast and so on. So this is a kind of active research area to do that. Yes. So I think yes, maybe last question before we switch.
Space, time, and seasonality. I have a question because, like, deserts, for example, would be more affected by seasonality. Winter is very cold, summer is very hot, but
Yeah.
humid environments are affected less. So how do you deal with seasonality effects in space, time?
Yeah, so you need to handle this as well. So typically, I mean, in time you would have some. So you need to put some trends, some kind of general effect. So you would have a trend that would depend on periodic function like sine and cosine with different periodicity. For example, to when you have data that change over the day, but then every day is a kind of similar pattern, you have to take this into account. So you kind of model this trend and typically remove it and then work on the residual that you get.
So you reach stationarity by removing the trend and then you...
Yes, exactly. So this idea of stationarity is that then the mean is constant. So if actually the mean structure changes through time or space, you need to model it, remove it until the residual are kind of approximately stationary. Yes. Okay, so thank you.